easy, but I have not shared the screen. Now you will be able to see the screen. Right. Okay, so another question. A be a ring. Okay, okay. Use basic open set in X equal to XF. Okay, V of F. Right. So spec of A minus V of F. Okay. Show AF capital A of U. No, but what is AF? The localization. Right. And what is AU? Right. Yes, but how is it defined? Ah, but okay, show that the ring AU equal to no, no. So we don't have to show this. This is just a definition. It is just a definition, and you have to show something about this. It depends on eh, not on that. Right. Ah, right. Depends. Some reason I don't know why it's not writing well. Only on you. Yes. Yes. Right. Right. Yes. 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 And this U is of course XF, but yeah. Mm-hmm. Okay. Yes, of localization, right? So you have a map from A to the localization, and if there is any B which inverts F, so phi, so if, so this is show if phi of F is a unit, sorry, then there exists a map, right? And you show that there exists a unique map, right? And since it's a universal property, it's enough to show that AG also satisfies the same property, right? So you've shown that if phi f is a unit, then pi g is also a unit. Uh, hmm. Right. Okay. Hmm. So if this is another basic open set which is contained inside, and show that there is an equation like this for some integer n greater than 0 and some u in A. So, okay, no, yes. So, right. So if xg is contained in xf, then we want to show that g to the power n is equal to uf for some u. Hmm. So this just means that if um this just means that if P is a prime that contains G, no, if P is a prime that contains F, then it also contains G, right? So if F is inside P, it implies that G is also inside P from the definition. Yes. Okay. Right. Uh Wait, so why is it equal? It should be okay, but s- so in right. Oh, it doesn't write. S- Stop. Oh, it's not writing anymore. Ah. Anyways, so yeah, so what were you saying? Yeah, you write on paper and check. So xf intersection xg is equal to x of fg, right? Yeah. And mm, yes, and this is fine because if you take the complements, then if okay, so if you take the complement, then if P is a prime that contains F, uh, then P contains Fg, and also if P contains Fg, then it contains one of them. Right. So this is correct. Okay. So then we know that x of Fg is equal to x of G. Uh, right. Yeah. So the radicals are the same. Right. And this means that so G is in the or yeah, right, right, mhm, right. So it means that yes, so it means the G raised to the power n is equal to some U times Fg, right? Okay, yes, right, okay, hmm. Yes, so that is fine. So that is fine. Let me just share this thing. Then this is gonna start working. Uh, yes, yeah. Maybe I'll try it on Jamboard and see if it works. And if it works, but it's okay. So then there is. Let me just share the screen. Oh, here it's working. So you can join. So you would have got a link in the chat. Yes. So now you want to define a homomorphism from AF to AG. Want to define a homomorphism from AF to AG, and uh, right. And what did we have? Yeah. So we had that this XF is contained in XG, and from here we draw the con this right. Yeah. Sorry, I just got the other. Just a minute. Right. Yeah. So XG is contained in XF, and G to the power n is equal to UF. Right. And from here you have a map. So how should that map be defined? You have something like f, a by f to the n. So you have to send it somewhere. Where will you send it? Ah, just like that. So, but then why is there a u in the numerator? Okay, yes, right. So we have a, um, right. So we have u to the, no, so this is some m. So we have u to the m and, no, u to the n, sorry, u to the n. No, what will it be? M, okay, okay, u to the m. So yeah, so okay, u to the m. So you have g to the mn is equal to u to the m f to the m. Right. So then we get g to the mn. So then you get this map, and right. So we have this map. Show that this map rho depends only on u and u prime, and this is homomorphism is called the restriction homomorphism. Right. So this is u and this is u prime. Yes, you can do that. So is this yes, yes, it doesn't depend on f and g. It only depends on u and u prime. Right. So it so this lies on the assumption of problem one, proof of problem one, part one. Yeah. So basically, this will be an isomorphism if you change the f, and the map will respect that isomorphism. Yeah. But anyways, first let's show the well-definedness. Yes, yeah, and but we can just say that if a times f to the m is equal to 0, right? So if A times f to the m is equal to 0, that means, what does that mean? It means that A times some f to the k is equal to 0, right? It means this, but that obviously will mean that A times g to the thing is also 0. So the map is well defined. Yes, so we have to do part 1 first. Otherwise, yeah. Yes, I think so. Yeah, yeah, and right. So just writing the map in the other direction. Right. And if we compose these two maps, if we compose these two maps, so let me write phi 1, phi 2. I should should get, let's compose and see. So phi 1 composed with phi 2 of a by f to the m. So that is phi 2 of a u to the m g mn. So that is, so this a prime is this. So there is a prime. Yeah, so this a prime times u prime to the power l. That's right. And g to the power, so g is raised to the power k, mnk, right? Yes. So we get this, and Now you can compare these things. So maybe like to u to the k, u to the k, then this is equal to g to the nk from the above thing. And so g to the mnk uh, g to the mnk becomes u u prime to the m, but there is another g, right? G to the m. uh, is this right? Okay. And u to the km. Okay. And this looks like a mess. Is equal to fkm. Right, in the denominator. So that is coming from second equation, but there is a u prime. So you mean u prime? Yeah, that's not a problem. So we have this equation and we have the other equation, which is um, right. Yeah, I think it's just u prime instead of u. So like this, and right. So g to the m, oh, yeah, g to the m, u to the m, u prime to the m, right. So I did in a different place. And the screens are very small, right? Okay, so right. So this thing will just become f to the km, right? F to the km, yeah, f to the km, and I don't know what's going to happen. I don't know. This is some. Yeah, yes, right. You can show that. Or more directly, yeah, it's probably equal, but just more directly, like you can see from here. So when you have this equation, right, it means that in AG, you are inverting U and F because G to the N is invertible. So if it's a product of two things, then those two are also invertible. Is that right? Yeah, product of, so if you have product of two things is invertible, then both the things have to be invertible, right? At least in a commutative ring. Hmm? Yes. But how do you just prove? Because it's not true in non-commutative rings. So that's why we should check it. It's true. So if AB is invertible, it implies A and B are invertible. Sorry, on the next board. So if you're on the top of the screen, yeah. So how do you just prove this? So there is right, yeah. So it's was obvious. I mean, I just confirming. Yeah, one-sided inverse, and so but it's not true in non-commutative cases. So, anyways, I just assume that you already saw it, so it's fine. So basically, in AG, F is invertible, and in AF, G is invertible, right? So basically, they have the same set of invertible things, right? So so basically, I'm saying that AF is basically S inverse R or S inverse A, and AG is also the same. But what is this S? So this S is like the saturation of the multiplicatively closed set Fn, right? So when you start, is yeah, so it's kind of left undefined, but you can define it. So basically, it's like the so given a localization of the ring A with respect to a multiplicatively closed set, the saturation of that multiplicatively closed set would be just all the elements that end up getting invertible in AF, right? And that you can rigorously define. So just A in A such that phi of A is invertible in the localization, right? So all of them, you can call that saturation, and it has other definitions also, but they are all one and the same. And this recognizing this is important to see that these localizations are equivalent, because that's the thing in localization, right? We localize with respect to a certain set, but actually more things get localized, and so we should always ask for what is the maximal thing that got inverted. Then everything becomes clear, right? So then we know this, and the question is, just a minute. Yes. So basically, we can just think of it. Just we can think of AF in terms of this S inverse A. Yeah. Then so that's the identification we make, right? But so I just want to see if this is canonical, meaning yes. So you have to define what is saturation, okay, and then you have to show that this is isomorphism, yes. Which is clear, but yeah, I'm not doing it. Okay. So this is the thing, and then yeah, now let's tackle the other question, that this so now this restriction morphism is so this yeah, so we have the restriction morphism from AU to AU prime is basically saying that it's basically based on the thing that um, that G inverts more things, right? So like when you localize with respect to G, then F also gets inverted, right? That is the meaning. But right, yeah, now let's just try to rigorously prove this, that this only depends that this map, let's do the calculation. So it's writing it once more. So we have this, and yeah, this goes to AU to the power M, G to the power Mn, where we had this thing. Uh, so if you write, so this is AU, so this is maybe you can write this as AF and write this as AG. AF and AG. Now, if you take AF prime and AG prime, then you want to show that the maps commute, right? So instead of that, I will just take this saturation. So this is SF inverse A and SG inverse A. And so there is isomorphism here and there is isomorphism here. And we would like to show that this map phi, which will be defined via this diagram itself, we would like to show that phi does not depend on f and g. Then it will be done, right? Because then you take some f prime and g prime for which then it will be, yeah. So they will all induce the same maps. So in particular, they will commute with this A because composition of two commuting things. Hmm. Or maybe they have something better, some better interpretation might be to no, we have already taken care of that because it's like we are sort of in we are viewing this S inverse A as a quotient of R cross R, but fine. We are viewing this S inverse A as a quotient of R cross R, right? Because that's how we define it, right? We take pairs and so on and so on. Yeah. And let me just erase this part because that might confuse because here AF is not equal to AG, but we have the following. Hmm. So how will this map turn out to be? So what is this map isomorphism from AF to SF, which I was not trying to avoid. Now we have to write that. Yes, but I think it is just if you just send AF to yeah, we can't really do anything but just send it like this, right? AF to the M to this. That's all, right? Yeah, and yes, and this thing is an isomorphism. That's fine. Yeah. Mm, yeah, it's a bit confusing. I mean, it's not. It's just that we are doing it. We are not finding the correct way to do it. But okay. So now let's just write this map phi. So phi of let's say a comma s, because now this s is not a power of f necessarily, right? We don't know that, right? So we have this, and we know that this is going to go to some some x, and then this is going to become mm, yeah, it comes down to that same calculation which you were saying, that we have to show that they are equivalent. It's the same thing. You have to just check it. But yeah. So this x can be, this s, you can multiply, divide by something so that it's uh yeah, it will be a factor of some power of f. So just write it like this, right? Phi of this, and this is same as phi of ax to the power f to the m. And then we send it to this, and we send this to a yes. So now we have to just write that same kind of thing. Hmm. Yeah. So it does not. I mean, this does not did not really help. So, but if we then in the previous board, if we have AF to AG, and I no. What were we doing? That was. I mean, that is no. It's slightly different. Slightly different, right? Yeah. This is slightly different. So this thing is equal to this thing or equivalent in AF, doesn't matter. And this thing we are sending to um yes, there is this U coming, but it's fine. Yeah. AX, U to the M, and G to the MN. So we just write that like this. Right. So so this is the image. And what do we need to show about this? So we need to show, mm, yeah, we need to show two things. One is that this does not depend on this f that we chose here. I mean, well, no. So sorry, there is as. I mean, it will not depend on this f because I mean it's a map, right? So it will not depend. So that's all right. Yeah, and we just want to say that this image. Yes, so the in the domain we have chosen things in a way that it doesn't depend on f anyways. But here we need to say that it doesn't depend on G. Hmm. Well, so, so we are getting this, and yeah, I don't want to go back to the same thing, but I think so. If we would have taken some G prime, then we would have got U prime, G prime to the power. Well, um, we can ensure that the M is the same. Yeah, so that's fine. We can ensure that. the m, we can ensure that, like we can adjust it with the u, because we are changing the u, so we can take the maximum powers. And so that's at least some, it will not actually to make a better our understanding, but yeah, let's see. Yes. So we have this, and then you want to just show that these two things are the same. So we have to create some space. Maybe I'll just go to the next board. Yeah. So we have this ax u to the m. Yeah, just a minute. Hmm. Ax u to the m. 1 minute. Still has to be shown, cannot be avoided. So we want to show that g mn, this is the same thing as a x, sorry, u prime m by g prime mn, right? We need to show these two things are same in S G inverse A. Yeah. Hmm. And so what is the definition? The definition is that we need to show that this minus this times g to the mn times some invertible thing, right? Some t is equal to 0 in A, right? And can we make any simplifications? Well, I suppose the A doesn't matter at all, and neither does the X, right? Because I suppose it will be 0 anyways without them. So let's just T, right, is equal to 0. But we know that this U is invertible, right? We know that this U is invertible in SG. That was the reason why we could actually do this map, right? So this U and U prime also, they are all invertible. Mm, yes, but then what is the relation between the U and the U prime? That we need to know. And then it will follow. So what is the relation? Let's just write that. So we know that G to the M is equal to UF, and G to the M prime is equal to, sorry, is equal to U prime F, correct? This is the relation that we know. And then I think it is clear. Yes. Then it is clear. So we just raise it to the power n, or, wait. Hmm. Little confused about the, I think we have done some mistake, right? We have mixed up the m and the n. So in, This one. Okay. This should be N. Yeah, that's a quick. That's a good way to correct it quickly. Yeah, that's how it should be. Right. Correct. So then it's fine. So we raise to the power m, and then you can see that it's true. And the f comes basically here, and is f is invertible. And that was the point. F is invertible in AG. That's why we could get a map, because I mean, if you're getting a map to something, then you would want your invertibles to be invertible there. All right. So yeah, and right. And so yeah, so if there are more invertibles, then yeah, then there are more primes containing it, sort of. Yeah. Anyways, yeah. But just let's see what is the intuition. So if there is like, so the open set of G is smaller, right? The open set of G is smaller. So if we think of this UF, so how should we think of UF, right? We should think of UF as the domain. Um, so let's just try to see if we can get some intuition. So we have UF, UG is smaller and UF is larger. And so this UG is the domain for what? So we have to, yes, but how do you say this? So if UG is contained in UF, then there is a map from, so we got a map from AF to AG, right? So, yeah, right. I don't actually know. That is the problem. Hmm. So this, right? So this AF should be thought of like, so A is like functions. If you think of the ring as a collection of functions, the elements of the ring as functions, and the primes as the points on which they are functions. Right, that's how we think. So then AF is the collection of, so AF is collection of those functions which are defined on UF, right? AF is those functions which can be defined on UF, right? So AF is, so in a way AF is like sitting inside R, in a way, or yeah, it's not sitting inside R, but in a way, if you think about the function, if suppose R was a domain, let's say R was a, yeah, then you think about the fraction field, then AF, AJ, they are all sitting inside the fraction field. Yeah. So you think of AF as functions defined on UF, and AG as functions defined on UG. So of course, if a function X is defined on AF, then you can just restrict the function to the smaller domain UG, because UG is smaller, right? And now, what is more rational for thinking of elements of AF as functions which are defined on UF should could be like this, without becoming too concrete, because then not be useful. So let's try. So if we think about spec R or spec A, so a collection of all primes, and AF is Yeah, so there has to be something which prevents definability, so becoming infinite. Right. So the elements of AF, sorry. So we should have a notion which prevents element being interpreted as a which we are interpreting as a function from being defined at certain prime. We should have a notion like that. Otherwise, what? Otherwise it's not. Otherwise, it's just symbolically declaring, right? Right? It's just like believing. Almost. So right. So if I yes, yes, no, they should at least be defined on U of F. Yes. So they could be defined on a larger thing. Okay. So I mean, if you take something like a by one, then I will say, yeah, let's build it like this. So a by one, and I will say things like a by one are defined on the entire ring. On sorry, on all primes, on all primes. Let's just build it like this. So yeah, things which are having one in the denominator are defined at all points. And if you have f in the denominator, then you will only be defined. Now this is almost becoming like a circular back calculation. So if it has f in the denominator, then it will only be defined at those primes which don't contain f. But this is almost like a definition. But now if you come to a concrete case, then it will be more believable. So if you now actually come to, let's say, interval 0 comma 1 and things like that, and it's actually quite used, it's quite related. So if we take this uh, continuous functions on closed interval 0 comma 1, okay, and now here the objects here are functions, but let's try. Objects here are functions. They are functions on 0 comma 1, and also, probably it's not useful here, but the maximal ideals of this are points of 0 comma 1. You can say, so the maximal ideals of C0 comma 1 are actually, so not the primes but the maximals, only the maximals. They are basically the points of 0 comma 1. Yes, yeah, right, that's right, yeah. So if you replace 0, so if you think of f as uh, uh, but then the problem is, yeah, if you think of f as a function on max of this, okay, yeah, so that we have prime, so we have maximal ideals. Now we don't have primes, but because the primes are very complicated, I do not know how they look like, but we restrict to maximal ideals. And if you think of f as a function not on 0 comma 1 but as functions on the maximal ideal, okay, um, right, then if you consider the if you consider yes, so no, but the problem is that the C0 comma 1 is not a domain. Yeah, it's not a domain. That is a problem. So you can, yeah, but okay, fine. I mean, why not? I mean, it's not a domain. It's fine, but you can. It's a ring. So you just call it as A. And now if you take AF, right? So what is AF? F is an element. So F is a function. So what is AF? Right. So AF will is just it's going to be formal thing, right? AF is just going to be formal because it will not be functions anymore, but they'll be formal. So AF, let's just write it. So AF will be like G by F dot dot dot, where G and F are contained. So now we have already interpreted. Yeah, so here this F should not be there because this is the general thing. So maybe some H as a function on, right? So AF is this. Yes. So so no. Yeah. So now, yeah, now if you look at UF, right? So what is UF? UF will be basically those maximal, it will be just a collection of maximal ideals, right? So instead of prime ideals, it will be a collection of maximal ideals. So those maximal ideals which don't contain F, right? And that is just basically those points of 0 comma 1 such that Fp is not equal to 0, right? And this basically means that UF is the domain for the elements of AF. Now it's concretely there, right? Yes, and this is like an abstraction of that, but the properties like restriction and all still go through, even though this is abstract situation which will incorporate situations which are not like this. But yeah, but it will, but it will still a lot of things like restriction and so on. You can still make sense here. So it's very nice in that sense. And I mean, obviously, the easiest example would have been just the polynomial ring, but I tried to avoid it. You can do it yourself, I think now. Yeah. So yes, yes. I think this was the point, right? To this was kind of the thing that changed the game. That you try to view the points of your space as functions on the spectrum. Okay, this is like everything. Like if you think about like this, if you see this geometry, algebraic geometry, they're trying to view things like this, trying to view points on this. Yes, right. And so let's see that. So in the next example, I think yeah, let's just go. Yes, because then it will be. I think that's what the problem is establishing basically, right? Yeah, that motto. Yeah, yeah. So let's just quickly go. I mean, I'm not write anything more, but let's just quickly go through it because yeah, the pre-shift thing would. I think that would formally make things clear more even. That's the language. So yeah. So we have this restriction map. Yes, and it is a pre-sheaf, right? Because it's a contravariant functor from the collection of open sets. So it's yeah. So in that sense, it is a pre-ship provided you verify these things. But let us see what is to be verified. Okay. So if u is equal to u prime, then the row is the identity map because then this u is one and n is one, so it will be identity map. And if you have this, then they will commute, right? And so it is fine. It's fine because we understand now. We are just restricting the domain of the function. Yeah. So yes. So this is fine. And now if x is equal to p with a point of x, right? So the space is x and p is a point. Then you show that, yes. So you basically have that, you have this thing, right? Where you basically take all the open sets that contain that point x, and then you just go smaller and smaller and smaller, right? And the functions which you get are basically all functions which don't vanish at p, or that's basically AP. Yeah, like all the, yeah, all the G's which don't contain P are inverted. That is AP basically, when you invert because you invert the complement of P. Right? Of course, you have to still write the proofs and all. Maybe that's fine. That's okay. Yeah. So this, and now as you say, so this assignment of this is called a pre-sheaf of rings because we are assigning rings, right? To every open set, we are assigning a ring. So it's a pre-sheaf of rings. And on the basis of open sets, this, and why is the V there? No, so V is just it's 5, it's not V, sorry. Says that the stock of this pre-sheaf, right, is the local ring AP. Yeah, it's clear. So does this pre-sheaf thing make it even more clear that these are functions? That's up to you, right? I I think it does. To me, it does in some sense. And in fact, the next step is, if you have not already done, is to basically uh, is to sorry, yeah, yes, yeah, is this. So is to construct a space which would serve as the codomain for these functions. You have the domain, right? All these A and these AFs, these all have domain. They all have domain inside. The domain is all X or subsets of X, right? Can you find a common codomain? Then it will be more clear, more sort of towards the philosophy that these are functions. So you should try to do that. That's called the sheaf space. But you can try to construct it on your own. And basically, the stock is the key ingredient. Yes, that might be useful if you try. I mean, even I don't remember exactly, but we can. But you try it and you can see. Okay. So yeah, it will be nice, I think. Yeah. So this is a pre-sheaf, and I don't know why is it not a sheaf. So for it to be a sheaf, I suppose you would require some more things. Maybe one point sets are closed or something. Yes. Oh, oh, it's indeed a sheaf, right? And it should be right. You're right. Yeah, it's correct. Okay, there are. So okay, yeah. So maybe some small axioms. Right. And then this is and this particular sheaf is called an affine scheme. So right, it's called an affine scheme, and then there is something called a scheme, which is the next thing, which probably is there in the next exercise. So yeah. So anyways, let's stop here. Yeah. And, yeah. Yeah. Oh, right, right. Yeah. Yeah, you should send me. And maybe next time also you can just tell me about it. And also that R is free thing. If you have not done, maybe you should just see and tell me next time, because I would be interested. So the last time we were doing a problem. So if you, yeah, if you may have, it's probably not very interesting, but you should, if you find it interesting, then you should just try it and tell me. Because I couldn't do. It's not. Yes, yes, yeah, things like that. So the main thing was that to me, what I remember is that if is R a free, no, yeah, no, we proved that R is not free, right? Over Z. Did we prove that? No, we did not prove that. Yeah, yeah. Did we prove that R is free or we not? Yeah. So yeah, and we were thinking that it is not, and we were not able to prove it. So so you should, if you try that. Yeah. Okay. Oh, that's great. Yeah. Okay. Bye. Bye.